Okay, hello everyone. Welcome to today's seminar. Today we are very happy to have George Kirklin from Okinawa, who's going to tell us about the Uhlmann phase, black hole information, and holography. So Josh, please, the floor is yours.
Great. So thanks to the organizers for the opportunity to talk. I'm really grateful for that. And also thank you to everyone for coming to listen to me. So I'm going to start by recapping something we're all very familiar with. So suppose we formed a black hole. This isn't a stable object because it loses energy via Hawking radiation, and so it will slowly decrease in size. And eventually, its size will be near the Planck scale. And at that point, higher order gravity, quantum gravity effects will take over. And in this talk, I'm only going to be interested in what happens before that point. So we can plot the entropy of the Hawking radiation over time while this process is happening. And Hawking's original calculations suggested that this is the line we should plot. But Page pointed out that if black hole evaporation is to be unitary, then the entropy of the Hawking radiation has to be less than this line. And this is just the Bekenstein-Hawking entropy of the black hole. So at a certain time, known as the Page time, we see that the Hawking curve is no longer consistent with unitarity. And this happens well before the black hole reaches the Planck scale. And if we therefore want to restore unitarity, we need to find a correction to Hawking's calculation after the Page time, so that the entropy of the Hawking radiation instead follows something like this, which is known as the Page curve. And this is exactly what's happened in the past couple of years with this well-known recent progress. So apparently the correct way to compute the entropy of the Hawking radiation is to use this so-called island formula. So here R is a fixed region of space containing the Hawking radiation, and I is another region which is called the island. And we're supposed to compute a set of extrema of a certain functional with respect to choices of the island. And then the entropy will be given by the minimum of that set. And the functional in question is given by an area term for the boundary of the island, plus the so-called bulk entropy of the combined region I union R. And roughly speaking, the bulk entropy is just the entropy of perturbative fluctuations on top of a fixed background geometry. So it's it's useful to draw things on a Penrose diagram. So here's one. So we're going to divide space-time into a gravitational region and an asymptotic region coupled together at a cutoff surface, as is shown. And we assume that gravitational effects only play a role in the gravitational region. This could be an exact assumption, so that the theories in the two regions are genuinely different, or it could just be an approximation. So the starting point is some matter that we allow to collapse to form a black hole, and then the black hole evaporates and it emits this Hawking radiation. And we use the island formula at a particular time by choosing a time slice of the asymptotic region. So here's one time slice we could pick, and this is an example before the Page time, and at that point the minimal island turns out to be empty. So the island formula then just reduces to the bulk entropy of the region R. And this is the formula Hawking used, so before the Page time the entropy will follow the Hawking curve. But after the Page time, enough entanglement, enough bulk entanglement will have been built up between the inside and outside of the black hole by the Hawking process, So pair production of particles, one goes in, one comes out, and this produces entanglement. And after the page time, enough of that will have happened that there's a non-empty minimal island inside of the black hole. And eventually this island will grow to span the entire black hole interior. Now, according to a variety of detailed calculations in different theories, the island formula seems to suffice to derive the page curve. And the validity of the page curve implies then that it's consistent to assume that the formation and evaporation of black holes is a unitary process. So this means that, in principle, all of the information that about what fell into the black hole can be recovered by measuring the Hawking radiation. But it's not immediately clear what form that information will take, and what measurements we should actually perform in order to access it. And the problem is that the whole formation and evaporation process really scrambles and encrypts the information, and we need a protocol for decrypting it. So in the main part of this talk, I'm going to describe such a protocol, and it's going to be based on an object called the Almond Phase, which is a generalization of Berry phase to mixed states. I'll show how one can completely reconstruct the phase space of fields in the black hole interior by making measurements of the Almond phase of the Hawking radiation. Combining this with knowledge of the classical field equations, this suffices to recover all of the classical information about the matter that fell into the black hole. So this result is actually a generalization of a previous one of mine in holography. So it turns out that by making measurements of the Almond phase of the state in a boundary subregion, one can reconstruct the classical phase space of the fields in its corresponding entanglement wedge. And the black hole information recovery protocol I'll describe combines the methods that led to that result with the insights that led to the island formula. So after talking about black hole information, I'll take a little step backwards. So one of the key features of gravitational systems is their high degree of entanglement. And I'd like to understand what role this plays in the Almond phase more generally. So to address that, I'll talk a little bit about Almond phases in generic, highly entangled systems, in particular describing the Almond phase in terms of a path integral. And in a certain limit, the action for this path integral appears to contain an extra dimension generated by modular flow. So this happens despite a lack of any assumptions about pre-existing holography in the system. So somewhat speculatively, I'll propose that this could be the basis of a mechanism for some kind of emergent holographic duality. But I should note that there are many unexplored aspects of this, so I don't want to concretely claim that this is holography in a precise sense. But it is tempting to conjecture that it could be, and it certainly seems worth exploring further. So here's an overview, here's a plan for the rest of the talk. So first I'll define what Almond phase is. Then I'll describe how you can compute the Almond phase of Hawking radiation and how you can use it to recover the information. And then finally, I'll describe the Almond phase of a generic highly entangled system. So if there are any questions at this point, now would be a good time. Otherwise, at any point during the talk, just interrupt and I'll be happy to try and answer.
Josh, I have a question.
Yeah.
So maybe it's not necessarily about what you're doing, but more generally, when you were talking about the page curve, people usually say that if you reproduce the page curve for the entanglement entropy, then this implies that you have a unitary process. But I think that's not exactly correct. I think having a page curve for the entanglement entropy is a necessary but not sufficient condition. What you would like to have is to have a page curve not only for the entanglement entropy, but for all the Renyi entropies. That would imply that the entanglement spectrum of the initial and final density matrices are the same, and therefore they are related by unitary transformation. So in general, it's not sufficient to just have a correct page curve only for the entanglement entropy, right? You need to have an equivalent thing for every Renyi entropy, and as far as I know, that hasn't been computed, right?
Yeah, that's an interesting point. I hadn't thought about the page curves for Renyi entropies. I definitely agree that having a page curve for the entanglement entropy isn't sufficient for unitarity. It's necessary, and I guess that sort of is a good point in the context of this, because the page curve has been shown to hold for the entanglement entropy, but that doesn't imply that the theory is unitary, so it doesn't imply that information is conserved. But what I'm going to describe is an explicit protocol for recovering the information. So that sort of does imply that at least at the classical level, the information is conserved. But yeah, it would be interesting to try and do these computations for Renyi entropy as well.
Okay, thanks.
Thank you. Okay, so I'll get going. So let me first define Almond phase. So as I said, this is a generalization of Berry phase. So first recall that the Berry phase of a curve of normalized states is defined in this way. So we have this curve of normalized states, and we compute this integral along it. Now, if the curve is closed, then the Berry phase is invariant under time-dependent phase shifts of the states. And we can view these phase shifts as U1 gauge transformations. And then the Berry phase is really just the integral of a U1 connection, which is called the Berry connection. Its curvature is called the Berry curvature. So besides this just being quite a natural object, the Berry phase, there's another reason to be interested in it in the classical limit. It's quite important in the classical limit. So such limits are often defined by specifying a space of quantum states, X, which approximately correspond to classical states of the system. And in the classical limit, the space of states is isomorphic to the phase space of the system. And it turns out that the symplectic form is just equivalent to the Berry curvature. So this sort of represents a precise sense in which a classical system arises from the classical limit of a quantum system. So the most basic example of this is probably given by the coherent states of a harmonic oscillator. So the Berry curvature of such states is just dq wedge dp, where q and p are the classical position and momentum variables. So another example is provided by holography. So in that case, the appropriate states are formed by inserting sources in the boundary theory, inserting operators. And then the Berry curvature is equivalent to the symplectic form of the bulk fields dual to those sources. So if we want to compute the Berry phase of a gravitational subsystem, we're going to run into trouble because gravitational systems are highly entangled. And this implies that gravitational subsystem states are highly mixed. but Berry phase is only defined for pure states. So if we want to do something like formulate a classical limit of a gravitational subsystem, we first need to find a generalization of Berry phase to mixed states. And this is where Almond phase comes in. So suppose we have a closed curve of density matrices acting on a Hilbert space. Let's pick a large number M of points distributed evenly along this curve, so that we get a sequence of density matrices, rho k. Next, let's pick an auxiliary Hilbert space, H prime. And then we need to come up with a sequence of states psi of k in the tensor product H times H prime, obeying these two conditions. So the first one says that psi k is a purification of rho k. So when we take the trace over the auxiliary space, we get rho of k. And the second one says that the transition probability from one state to the next should be maximized, subject to the first constraint. And then in the limit as m goes to infinity, we end up with a curve of states in H times H prime. And one thing that is important to note, and that I've drawn here, is that even though the curve of density matrices was closed, this new curve doesn't have to be. So after coming up with the curve of purifications, psi of t, we can finally define the Uhlmann phase. So it's just the Berry phase of the purifications with this additional factor in front. So there's an equivalent way to write this in terms of the discrete set of the discrete states along the curve in this way, and this will be useful later. And I should note that although there is some freedom in the choice of the purifications that go into computing this Uhlmann phase, it's possible to show that the Uhlmann phase itself is unaffected by this choice. And this sort of invariance under different choices of purifications is a generalization of the U1 gauge symmetry that appeared when we defined the Berry phase. And when the curve of density matrices is pure, then the Uhlmann phase reduces to the Berry phase. So it's really a generalization of Berry phase. All right, so now I've defined what the Uhlmann phase is. It's a generalization of Berry phase. Berry phase gives us access to the classical physics of a pure system. So maybe we can hope that the Uhlmann phase will give us access to the classical physics of a mixed system. So that's something I'll show in this section. So I'm going to talk about how to compute the Uhlmann phase for states of Hawking radiation. And I don't have time to go into every single detail here, but I'll try to give you an overall flavor for how the argument works. So as I mentioned previously, in the setup, we're splitting spacetime into a gravitational and an asymptotic region. And we'll assume that the total Hilbert space factorizes into Hilbert spaces for those two regions. States in this theory essentially amount to the specification of some boundary conditions on a space-like surface. And we can compute the inner product of two such states in terms of partition functions in this way. So the denominator is here because I'm assuming that these states are normalized. And at this stage, I'm restricting to Euclidean partition functions. But at the end, everything's going to be Wick rotated to Lorentzian spacetime. And it's just simpler to start from the Euclidean perspective. So we can compute the partition function in the semi-classical limit in terms of an effective gravitational action and a partition function for the quantum fields on a gravitational background using this formula. So M here is a manifold with metric G, and this manifold of metric, as well as all of the fields, have to obey the boundary conditions lambda1 in the Euclidean past and lambda2 in the future. And the future boundary conditions are additionally complex conjugated and time reversed, which is what star t is supposed to denote. And because this is a semi-classical limit, the partition function here should be computed in a saddle point approximation. So in other words, we should evaluate it on the manifold and metric, which minimize it. So to get the density matrix for the state in the asymptotic region, we just take the trace over the gravitational part of the Hilbert space. When we computed the inner product, we summed over degrees of freedom everywhere in space, which is sometimes called gluing. Conversely, to get the rho of lambda, we just sum over degrees of freedom in the gravitational region. Now, since the Hawking radiation is all collected in the asymptotic region, we can really just think of this density matrix as the state of the Hawking radiation itself. So now suppose we have several such states of radiation corresponding to different possible boundary conditions. And this really means we have several copies of the system. If we compose these density operators one after the other, this means that we're gluing the asymptotic region of each copy to the next one. And then if we take the trace of the whole thing, that means we're gluing the asymptotic region of the final one back to the first. And we can again compute this quantity in terms of partition functions. And the boundary conditions for the partition function in this numerator are given by gluing together the n copies cyclically in the way I've just described. So a bit more precisely, in the semi-classical limit, the partition function may be written as before, but now the manifold Mn and the metric G and the fields have to obey this different set of boundary conditions. So here's an example of what this would look like in the case of n equals 3. So we have 3 copies of the Euclidean past, 3 copies of the Euclidean future, and we glue these all together cyclically in the appropriate way. But really, so this is one example, but really the key insight that led to the island formula, at least in this semi-classical setup, is that we should allow all of the possible topologies that connect the different gravitational regions in the partition function. So for example, we could have a configuration that instead looks like this. And so there's a wormhole connecting the first and third copies. And these kinds of wormholes are known as replica wormholes. And there's been a lot of discussion about whether these are actually the right thing to do, whether you should actually include these topologies, what it means for the theory in terms of, are we just talking about one theory or are we talking about an ensemble of theories? I won't discuss any of that. I'll just assume that we're supposed to include these replica wormholes. Okay, so I want to give some indication of how this leads to the island formula. So one can compute the von Neumann entropy of rho with a replica trick, which means we can first compute the trace of rho to the n for integer n, and then we can analytically continue in n and use this formula. And the boundary conditions are now the same for all of the n copies that contribute to the trace of rho to the n. And this means that there's a Zn symmetry that cyclically permutes the n copies, known as replica symmetry. And we'll assume that this symmetry isn't spontaneously broken, so that it continues to hold away from the boundary as well. And then the general form of the on-shell configuration that dominates the partition function will look a little bit like this. So as you can see, there are n copies of the boundary conditions, and replica symmetry acts by cyclically permuting them. In addition, there's this replica wormhole that connects the different gravitational regions. And then replica symmetry fixes a certain codimension 2 surface, which I've labeled upsilon. And this is the boundary of n codimension 1 regions I. And these different i's are all cyclically permuted by the replica symmetry. So at this point, we can, because we have this n-fold symmetry, we can quotient this configuration by the action of the replica symmetry. And what we end up with is just a single copy of the original system. So I've now drawn in R and the island I. And there are a couple of important features of this copy, of this single copy. So first, there'll be a conical defect at the boundary of the island. And second, we need to insert twist operators at I and R in the QFT that lives on this space. So now one can analytically continue in N, and one can follow through on what this means for the entropy. And it turns out that the conical defect at the boundary of the island contributes an area term, while the QFT twist operators contribute the bulk entropy term. And because we're doing everything in a saddle point approximation, there's also a minimization and extremization that takes place. And the end result is just the island formula as advertised. So obviously I've skipped some details, but this is the main thrust of the argument. And now I'm going to apply some similar techniques to show how to compute the Almond phase of the Hawking radiation. So one key result we'll need is this theorem, also due to Uhlmann. And this says if we have two purifications, psi and psi prime, of two density matrices, rho and rho prime, then that means that those purifications maximize the transition probability if and only if this equation is satisfied. So this quantity on the right-hand side is known as the fidelity of rho and rho prime. And I'll show how to compute it for Hawking radiation states, and then how to find purifications psi and psi prime such that the theorem is satisfied. So to compute the fidelity, we can use a replica trick. So we can take this thing inside of the trace, do it to the 2kth power, and then we can use the cyclic property of the trace to write this in this way on the bottom line. And then we can compute this thing using partition functions and effective gravitational actions, and then we can analytically continue back to k equals half. So in terms of partition functions, we can write this correlator in this way. So there are now 2k copies of the original system, and the boundary conditions alternate between lambda and lambda prime, which are the boundary conditions coming from rho and rho prime. And if lambda equals lambda prime, then we have the same replica symmetry that we had previously, which is so a full Z2k replica symmetry. But when lambda isn't equal to lambda prime, the Z2k is broken down to a ZK. So it cyclically permutes twice, so that the lambdas match up with the lambdas and the lambda primes match up with the lambda primes. So we can't quotient by the full Z2k, we have to quotient by the ZK subgroup. And since we're dividing 2k copies of the system by k, we're left with just 2 copies. So that means there's 2 copies of the boundary conditions, as you can see. And as before, we're allowed to have these replica wormholes that connect the 2 gravitational regions. And there'll be this codimension 2 surface, upsilon, which is a conical defect. Actually, on these 2 remaining copies, there's actually an additional Z2 symmetry. And the action of this symmetry is to reflect the whole thing in the way shown, and also to complex conjugate the fields. And this symmetry fixes a codimension 1 surface, which passes through the conical defect. So it's useful to decompose that codimension 1 surface into these 2 parts, n plus and n minus. So we have 2 copies, but really we want to reduce that down to 1 copy. So let's imagine cutting along this codimension 1 surface in green. And we end up with these 2 pieces. If you can imagine that, you cut along here and then flatten everything out. So actually the contributions to the partition function from these 2 pieces are complex conjugate to each other. So we really only need to focus on one of them. So let's take the one on the right. And I've now drawn in the asymptotic region R and the island I. And it will turn out that this island I is exactly the same one that plays a role in the island formula. Now on this manifold, there's a discontinuity in the fields as you go from n minus to n plus. And you can think of this discontinuity as being implemented by the insertion of an operator, u lambda lambda prime, on a surface n, which lies in between n minus and n plus. And actually, the Z2 symmetry that I mentioned previously is sufficient to guarantee that this operator will be unitary, or at least that it can be well approximated by a unitary operator in a semi-classical limit. So if we do a bit more work with this, after analytically continuing to k equals half, one finds that this equation holds. So we take that operator that implemented this discontinuity in the fields, and we just insert it between the 2 original states, and we get back the fidelity after taking the absolute value. Now, this operator u lambda lambda prime only acts in the gravitational region. So that means when we trace over the gravitational region, the action of that operator doesn't affect the density matrix that we end up with. So if we define these 2 states, psi and psi prime, these will be purifications of rho and rho prime. And therefore, if we invoke Uhlmann's theorem, we can conclude that these states maximize the transition probability while still being purifications of rho and rho prime. So now we can use this result to actually compute the Almond phase of a curve of Hawking radiation states. So we pick density matrices rho k evenly distributed along the curve, and we can construct these operators, these unitary operators uj, for each subsequent pair in the way I've just described. And then we just write down these purifications. So psi naught is lambda naught, psi 1 is u1 dagger lambda 1, psi 2 is u1 dagger, u2 dagger lambda 2, and so on. And by the reasoning that I've just described, these purifications maximize the transition probability from one state to the next. And they are genuine purifications of the appropriate density matrices. So this means we can use these purifications to compute the Almond phase. And if we substitute everything in, this is what we get. And I'll skip the details, but at this point, it's actually relatively simple to take a semi-classical limit and compute each term using the actions of on-shell field configurations. So if we use covariant phase space techniques, in particular, one can find that the Almond phase can be written in this way. So here, I've introduced some notation. So phi j is the dominant field configuration corresponding to the state lambda j. Delta phi is the change in field configuration as you go from one state to the next. Capital theta, I union r, is the symplectic potential for the fields in the island and R. Now we can take the limit as m goes to infinity, and this sum just converts into an integral. So it's the integral of the symplectic potential along the curve of field configurations corresponding to the curve of states lambda t. And I should say that at this point, the Wick rotation that I mentioned earlier has taken place. So these field configurations are the Lorentzian field configurations. So in this way that I've sort of derived, or missing out details, like I say, we have a direct connection between the Almond phase of the Hawking radiation and the classical phase space of the island. So let me now describe how an observer can actually use this to recover classical information from a black hole. So suppose we have a space P of possible initial matter configurations, and we'll assume that each configuration eventually collapses to form a black hole. Moreover, we'll assume that the classical fields outside of the black hole are the same for each initial configuration. So this means that a naive classical observer who can just measure the classical fields in the exterior won't be able to recover any information about the initial configuration. But now let's see what happens if we consider Almond phase. So let Q be the space of possible states for the Hawking radiation after the page time. So once an island has formed. So a less naive observer is able to measure the Almond phases of paths in Q. And by our formula for this Almond phase, that observer therefore has access to all of the components of the symplectic form of the fields on the island. And if you can measure all of the components of the symplectic form, that means you can measure all of the Poisson brackets that you want. And in practice, this means you can basically carry out arbitrary classical experiments on the island fields. So if the observer waits long enough, the island will span the entire black hole interior. And then that means that they can perform arbitrary experiments anywhere inside of the black hole, or at least anywhere where the fields are still classical. So they couldn't get near to the singularity. They can then take the data from those experiments and use it to determine the classical state of the matter in the black hole. And then they can run the Einstein equations backwards, maybe by simulating them on a classical computer. And this would allow them to deduce the initial matter configuration. So in this way, all of the classical information is recovered. So this is the end of the main part of the talk. If there are any questions about about this, now might be a good time. Okay. So I'm now going to talk about something that's somewhat more speculative. So one key feature of gravitational systems that has become increasingly important in the past couple of decades is the fact that they're highly entangled. And it's in fact widely believed that this high degree of entanglement is at least partially responsible for the emergence of space-time. So to explore this, I'm going to present a formula for the Almond phase of a generic highly entangled system. And I won't make any assumptions that this system is holographic, but nevertheless, we'll see that the formula has some suggestively holographic features in the classical limit. So let's consider a generic system with a Hilbert space H. I'll assume that there is a classical limit in terms of coherent states. And different people mean different things by coherent states. All I mean is that there is a classical phase space which maps into states in the Hilbert space, and that there's a resolution of the identity in terms of those states. And also that in the classical limit, the Berry curvature of these states should be proportional to the symplectic form of the classical phase space. And proportional now because I'm explicitly including the factor of h bar that I left out before. And it'll be useful to just pick some canonical coordinates for the symplectic potential, pi and qi. So suppose we have a closed curve of density matrices acting on H. There's a formula that was known to Uhlmann in the 1980s, which can be used to compute the Almond phase in terms of a certain path-ordered exponential. And the thing that you path-ordered exponentiate is these operators A of t, which obey this equation here. And the dots over the square roots of rho denote differentiation with respect to t. So I'll assume that the density matrices are invertible just for simplicity. Then this equation for A has this integral solution. And this can be confirmed just by substituting it in to the equation, and then you can just do the integral. So by inserting many resolutions of the identity in this path-ordered exponential, you can write it as a path integral over paths of coherent states, just in the usual way you construct a path integral. And the action for the path integral takes this form. So the first term in the action is the Berry connection. And in the classical limit, it's just going to give the symplectic potential of the classical phase space. But there's the second term involving A, which is really the interesting bit. So what happens to that? So to address that term, it's useful to write A in a different way. And it's possible to show that you can do this. So you can write it in this way. It might look more complicated than the previous form, but it turns out not to be. And the reason is that it expresses things in terms of objects we might be familiar with. So K here is minus log rho, so that's the modular Hamiltonian of rho. And this map parameterized by alpha, taking O to rho to the power of I alpha O, rho to the minus I alpha, this is just known as modular flow. And in gravity, the modular Hamiltonian of a subsystem goes like the inverse of h bar, So let's take that as inspiration and assume it's true here as well. This means that rho is highly mixed in the classical limit. And furthermore, you can show that it implies that in the classical limit, modular flow just reduces to a kind of classical flow in the classical phase space. So from this scaling, you can deduce that A itself is also order 1 over h bar. So both terms that appeared in this action are order 1 in the classical limit. Now, if we substitute our expression for A into the action and do some manipulations, you find out that the action takes this form, where these states x of t and alpha are defined by acting with modular flow on x of t. And because modular flow reduces to classical evolution, x of t and alpha is just it just corresponds to a single classical state. So we can observe that this integrand here is proportional to the Berry connection of certain curves of states. And if we substitute in the symplectic potential in terms of the canonical coordinates of the classical state x of t and alpha, we get this equation at the bottom of the slide that so the action in terms of the canonical coordinates of these states generated by modular flow. This is a Hamiltonian action. So this is just a particular kind of symplectic potential that's integrated along a curve. And the symplectic form is this. So if we compare to the original symplectic form, we can see that there appears to be an extra dimension's worth of degrees of freedom. And these are parameterized by alpha. So in capital omega, we're integrating over alpha with a certain measure, sech pi alpha. And we're integrating over all of these degrees of freedom. Of course, the degrees of the p's and q's at one alpha won't be independent of the p's and q's at another alpha, but instead they're related by modular flow. But that's not necessarily a problem, because we can interpret that perhaps as a gauge symmetry. But I don't want to dwell on that too much. So with this sort of bare bones argument, this seems to be hinting at a mechanism for some kind of emergent holography. So if we compare what's happening here with known results from holography, we can see there's some correspondence. So in particular, the Almond phase and the modular flow probes the bulk in exactly the same way in holography that they do here. Also, in both cases, the modular Hamiltonians have the same scaling. But on the other hand, what I've described is really far from a detailed picture. And there are many outstanding questions. So perhaps the main question is, why should the holographic bulk only appear in the Almond phase? It should appear in other quantities too, like transition amplitudes and correlation functions. I don't really have many answers or time to go through the few answers that I could give to this question, but I will comment that the answer probably has something to do with decoherence. And this is because of the key role played by transition probabilities in the Almond phase. In order for the Almond phase to be relevant to other quantities, in order for the Almond phase to be relevant to other quantities so that the holography plays a role more broadly, there needs to be a reason for transition probabilities to be relevant to those quantities. And this is exactly what decoherence does. It causes transition probabilities to play a role in the general dynamics of a system. So let me summarize what I've told you about today. So first, I showed how one can derive the formula for the Almond phase of the Hawking radiation in terms of the classical phase space of the island. Then I explained how one can use this to carry out arbitrary classical experiments in the black hole interior, and therefore to recover all of the classical information that fell in. And then in the last part, I derived a path integral formula for the Almond phase of a generic highly entangled system. And I explained how it appeared to involve an extra dimension in the classical limit. So here are some open questions on these topics that it might be interesting to explore. Thanks for listening. If there are any questions, I'd be keen to hear.
Okay, thanks, Josh. We have time for questions.
Can I ask a question?
Yeah, hi, John.
Hi. I'm not sure I understand very well what the types of measurements are that you need to do in the Hawking radiation to reconstruct the semi-classical island physics. Could you elaborate on that? Because I thought we knew this was possible in principle, but it would require very complicated operations on the Hawking radiation. In your case, is that also true, or are you doing something else?
Yes. So I've given you a quantity that you're supposed to measure. It's the Almond phase. But I guess what you're asking is how operationally, like how would I actually go about measuring that thing, and how complicated would it be? Is that?
That's right, because you're suggesting something operational, right?
Yeah. So I should say that there have been suggestions on how you set up experiments to measure Almond phase. I don't remember exactly the authors of those papers, and there have also been it's also been like explicitly measured with an experiment for a simple system. So this is something you can measure. Now the question of the complexity, if you notice, this is my last open question. That's something I'd be very interested in understanding how difficult it actually is in practice for a system with a large number of with a large dimension like a black hole system. How difficult it actually is to measure to an experiment that measures this Almond phase. I don't have any clue really.
Yeah, but it's just a number, right?
Mm-hmm.
For a given one parameter family of density matrices, it's a number.
Mm-hmm.
So are you supposed to have infinitely many identical copies of the black hole and the radiation system at your disposal in order, and then do you have to perturb the system in order to actually, suppose I want to ask one of those standard black hole questions, namely, is there a pink elephant behind the horizon of a black hole or not? What would be the operational way to settle that question with the Uhlmann phase?
Right, okay, so so to answer questions like that, you sort of need a reference. You need to be able to say, here's a state that doesn't have an elephant, here's a state that does have an elephant. Now, how do the observations that I can make between these two states, how will they differ? And this is what the symplectic form tells you. You integrate the symplectic form along some curve or on some two-dimensional surface in phase space, And as so long as you do you do it along the right curve, this is exactly what it's telling you. It's telling you how your observations will differ between a 0.1 in the phase space and a 0.2 in the phase space. So that's the sense in which I'm suggesting that this allows you to do to make classical measurements. I guess I could say also, if you know the symplectic form, which according to this result you can get the symplectic form by just computing the Almond phase for lots of little loops in the space of possible Hawking radiation states. If you know the symplectic form, then you know all of the Poisson brackets, and the Poisson brackets they're really what tell you like how your measurement, like if you do some experiment, how the system will react to that experiment, and how your measurement apparatus will read something out. So
yeah, but if you want to examine arbitrary loops in the space of possible Hawking radiation, then basically what you need is a large reservoir of all possible black holes that you can make with arbitrary initial conditions, and then you have all these types of Hawking radiation, and you can try to maybe combine or glue together a bunch of states of Hawking radiation and make that loop. But in a given quantum system, you cannot engineer a particular loop in Hawking radiation space. Right?
Yeah, you can say the same thing about a state, just a completely classical system, no black holes or anything. If you're not allowed to change the state, then you can't. It's irrelevant that there's a symplectic structure in your phase space, because you can never measure anything if the state can never change. You're just coming up with a set of numbers that don't really correspond to anything. You need to be able to consider the differences between different states. And maybe I'm wrong about this. Maybe it's just a philosophical question of what it means to be able to measure something. You can either say, if you have a single quantum state or just a single classical state, that's enough to talk about measurements. Or you could say, I'm only allowed to measure changes between one state and another state. So instead of just saying, this is a state and I'm telling you it has an elephant in it, I can be like, I have two states and this second state has one more elephant than the first state. But I'm not sure if the question you're asking really depends on the fact that this is a black hole setup. I think it's more of a question of, if you have access to the symplectic form, the components of the symplectic form in some classical phase space, is that enough to determine the classical state? And I guess I'm telling you have access to the symplectic form.
Yeah, no, my question was whether simple measurements of the Hawking radiation are sufficient to do simple semi-classical measurements in the interior, because that is not what other people would say is true.
Yeah, I don't know if I don't know if they'll be simple. This is my last question. It's, in general, I would expect this to be quite a complex procedure. Nevertheless, it is a procedure that you can do.
If I may ask another quick question about these highly entangled states at the end. So
yeah,
how different is this from, for example, is this a bit like, so in highly entangled state, you could imagine in the bulk looks a bit like a black hole or has a horizon or something like that. Modular flow is then typically the boost generator near the horizon. Are you basically reconstructing that boost generator in your final bit, or is it something completely different?
So I'd love to know the answer to that question. It would be very nice if that were true, because you would have two ways of constructing the action, one just coming from the holographic path integral, one coming from this path integral. and it's not immediate that they have to be the same action, that you've done everything in the same, you've described things in the same way. But if it turns out that these actions are actually the same thing, then the modular flow that happens here has to be the same as the modular flow that happens in those kinds of states, and it would play the same role in the action. So yeah, I think to understand whether this is actually anything like emergent holography, that's the kind of question that would need to be addressed.
Okay, thanks, Josh.
Thank you.
I also have a question, if I may ask.
Right.
I wanted to ask about connections to other proposals for entanglement wedge reconstruction. There's, for example, these PETS maps and other stuff. Is this related to your work?
So I haven't thought too hard about that question, but I am interested in the answer. One thing that's I guess different about this is that so this is sort of explaining how to recover the classical phase space, whereas I guess in general these reconstruction arguments, you would want them to work for the whole quantum, the whole set of quantum information that you might have access to. On the other hand, no, I won't say that, but yeah, that's something I'd like to understand more. I mean, if all these reconstruction methods are all valid, then clearly they should be related in some way. So yeah, it'd be good to understand that.
Okay, thanks.
Adrian has a question.
Yes, hello. So I have two questions actually, because I'm a bit confused. So in the context of Berry phases, I'm used to studying the Berry phase that one picks up studying a loop of states when this is due to a Hamiltonian that is cyclically changing, right? But I think here you seem to be talking about closed loops of density matrices without necessarily making reference to an Hamiltonian, right? So I'm a bit confused about that.
So you're right. The original definition of Berry phase, you have a Hamiltonian, and you focus on the ground state, and you assume that the ground state is non-degenerate, and then you vary the Hamiltonian slowly around a closed loop in parameter space,
right?
And that means that the ground state of the Hamiltonian also varies around a closed loop. And if you compute the change in the phase of the ground state under this adiabatic evolution, you see that there are two terms, and one is just the Hamiltonian, the ordinary phase you'd expect, and the second one is this Berry phase. And the Berry phase there is just the formula I've given for the Berry phase here, but you compute it for that closed loop of ground states. So this formula is really a more general version of that original definition. But you don't really need to make reference to a Hamiltonian to compute these general Berry phases.
I see. Okay. So that maybe answers my second question, because I was going to ask to what extent the adiabatic approximation is good in the context of black hole evaporation.
Yeah, I'm not sure exactly, because when you define Berry phase more generally in this way, you don't really need to talk about adiabatic change.
I understand. Yeah. Okay. Thanks a lot.
Cool. Thanks.
Well, okay, if there's no more questions, then we thank Josh again for his talk. Thank you very much.
Thank you.